We on?
Yep.
Hi everyone, I'm Stephen Capasso. I'm going to solve problem 2 from homework 1. First I'll read it to you. Prove or disprove if the probability of A given B plus the probability of A bar given B bar is equal to 1 if and only if A and B are independent. A couple of conditions: probability of A is greater than 0, less than 1, and same for probability of B is greater than 0, less than 1. To proceed, we have to define our conditions for independence. For independence, we require probability of A, B equal to probability of A times probability of B. This is this is an intercept, and here we're multiplying the two probabilities. Right, so we need to evaluate this and setting it equal to 1 and see if we could meet that requirement algebraically. So what we're going to do, and let's just get a visual of that. Let's draw the space, the decision space here, and something for A, something for B, circle for A, circle for B. And what is it that we're trying to do? We want to get the probability of A intersect B, which is that there, to equal the probability of A times the probability of B. It's always good to have a visual. Anyway, so, but here's something equally important. This term, this is the problem term right here, because it has these complements in it. We have to find a way to algebraically get rid of those complements. So we need to get probability of A bar, B bar in terms of A and B, no complements. I think that's key. So, probability of A given B, this sort of form, plus probability of, I'm going to do this, A, B, and whatever it takes, all of that is going to equal 1. From there we can do some algebraic manipulation and attempt to achieve this form. So, next, we know from conditional probability that the this term, probability of A given B, can be expressed as the probability of A intercept B over the probability of B. But the problem is that the probability of A bar given B bar, this is equal to probability of A bar given B bar over probability of B bar. And these complements make it impossible to prove that out. So we have to use some tools to manipulate them so it looks like that, hopefully. Anyway, so that being said, right, so I'm going to write one more thing here that's pretty important. From Axiom 3, page 210, page 20 in Kapolis, the probability of, we can infer that the probability of B complement is equal to probability of A bar B bar plus probability of A B bar. And this is good because this contains the thing we need to try to isolate and solve. This A bar given B bar. And So what we're going to do is I'm going to erase all of this, and I'm going to start with that. Get rid of all this stuff. I'm going to save this because we don't need this anymore. So now, all that being said, we need to solve for probability of A bar B bar is equal to probability of B bar minus probability of A intercept B bar. And from here we have to use some identities. This probability of A B bar is equal to the probability of A times the probability of A, bear with me, times the probability of 1 minus probability of B. Where did we get that? We got that from the previous statement that had probability of B bar. We know the probability of B bar is the same as 1 minus probability of B. All right, so that's our first attempt to eliminate the complements. And then from there, we're also going to say that, and this is equal to the probability of A minus probability of A intercept B. Okay, we're going to put this back into one of the previous equations. We've already solved for AB, so that now we're going to have probability of A bar B bar is equal to 1 minus, I did another here, I did another insert for the B bar, 1 minus probability of B minus probability of A plus probability of AB, which we got from here. Now, we have this in terms of no complements. So let me just say that, no complements, no bars, and that's good. We achieved, that's what we want to achieve. So from here, we're going to go back to the master equation up there and put that in terms of our conditional ratios. So we have probability of AB over probability of B. That one's fine. Plus, now we're going to insert this whole mess. 1 minus probability of B minus probability of A plus probability of A intercept B over, because we have to get that probability of, 1 minus probability of B, that was another insert, and all this has to equal 1. This can get a little messy, so it's just algebra though. Probability of AB times 1 minus probability of B plus probability of B times 1 minus probability of B minus probability of A plus probability of AB intercept is equal to probability of B times 1 minus probability of B. Okay, now we're going to see that some things nicely cancel out. Let's see if we can do that. Let's do one more line below this. So probability of AB minus probability of AB times probability of B minus probability of B squared. And this could, this actually should be probability squared, maybe not B squared. That's open to interpretation. Minus probability of A times the probability of B plus probability of A intercept B times the probability of B is equal to probability of B minus probability of B squared. That should be P squared B. No, I think it's better to have that probability squared B. It's the same thing, right? Now we can do our cancellations. What do we see cancels here? This cancels out with this, and also this cancels out with this, and then we're going to be left with one more thing supposed to cancel out. Oh, did I leave out a term? Probability of AB, bear with me. AB, probability of B, plus probability of B. Yeah, in here it was supposed to be plus the probability of B, and minus probability of B squared. I got that in. I'm sorry, I made a mistake. So that cancels that, and what's left is this and this, and we're going to put them together and set them equal to 0. So we end up with probability of AB minus probability of B of AB minus probability of B times probability of A equals 0. Oh, we put them on the other side. Get rid of the put them on both sides of the equality sign. So we have probability of AB is equal to probability of B times probability of A, and that's it. That's our proof right there. So some of that got a little sloppy. I apologize. So this is our proof. We did it. We got to this point. It was a little tedious, but we're there. So I'm going to say QED. That's Latin for as shown or demonstrated. And as a result, therefore, we could say that A and B are indeed independent. That's it. Okay.